Ever wondered how your smartphone can recognize your voice or how your email filters out spam? These are just tiny examples of how deep learning is impacting our daily lives. Every day, without even realizing it, we are interacting with deep learning technologies. When you ask your virtual assistant for the weather, deep learning is at work. When your email service separates unwanted messages into a spam folder, that's deep learning too. It's in the way our cars are becoming more autonomous, how our devices can identify objects and faces, even in the recommendations we receive when shopping online or streaming our favorite shows. But what is deep learning? How does it work? And why is it so transformative? These are the questions that often swirl around this buzzword. But fear not. Over the course of this video, we're going to demystify deep learning, breaking it down into bite-sized, digestible pieces. In the next few minutes, we'll delve into the fascinating world of deep learning. Deep learning, a buzzword you've probably heard, but what exactly does it mean? Let's dive into the world of artificial intelligence to find out. Deep learning is like the whiz kid of machine learning, a concept that's all about computers learning from data. Picture machine learning as a toolbox full of instruments, algorithms, each with its unique role. These tools help computers identify patterns, make predictions, and essentially learn from experience, much like we humans do. Now, amongst these tools, there's one that's particularly powerful. That's deep learning. So what sets deep learning apart from the rest? It's all about the depth. Deep learning algorithms dive deeper into data, extracting layered, intricate patterns that other machine learning tools might miss. At the heart of deep learning is a fascinating piece of engineering called an artificial neural network. This is a computing system inspired by the human brain, designed to mimic how we think and learn. Just as our brain is made up of billions of interconnected neurons, an artificial neural network consists of layers upon layers of artificial neurons, or nodes. Each layer of nodes performs a specific task, transforming the data it receives from the previous layer. The first layer deals with raw input data, like pixels in an image or the audio frequencies in a voice recording. As the data moves through the network, each layer extracts more complex features. By the time the data reaches the final layer, the network has identified the patterns or features necessary to make an informed decision or prediction. And the beauty of deep learning is that it's self-teaching. The artificial neural network automatically refines and optimizes the features it extracts, eliminating the need for us humans to manually engineer these features. So whether it's recognizing a face in a photo, understanding spoken language, or predicting the stock market, deep learning is there, making sense of the world's data. In essence, deep learning mimics the human brain to solve complex problems. Now that we have a basic understanding of deep learning, let's dive deeper. We'll start by exploring the different architectures of deep learning models. These models are the backbone of deep learning, providing the foundation upon which all its functionality is built. First on the list is deep neural networks, often referred to as DNNs. These are essentially networks composed of multiple layers of artificial neurons. Each layer is designed to extract a different, increasingly complex set of features from the input data, allowing the network to understand the data in a layered, hierarchical way. Next, we have deep belief networks, or DBNs. These are generative models with multiple layers of hidden variables. Each layer's variables are connected to those of the layer above, but not to each other, creating a unique structure that allows for the learning of complex, high-dimensional distributions. Then there are recurrent neural networks, also known as RNNs. These networks have a unique feature. They have cycles in their connectivity structure. This allows them to effectively process sequential data, making them particularly useful in areas like speech recognition and language processing. Fourth on our list is convolutional neural networks, or CNNs. Inspired by the human visual system, these networks are designed to automatically and adaptively learn spatial hierarchies of features. This makes them exceptionally good at tasks related to image and video processing. Finally, we have transformers. These models, unlike the others, do not rely on recurrence or convolution, but rather on self-attention mechanisms. They have been particularly successful in natural language processing tasks, where they can understand the context and semantics of language by focusing on different parts of the input sequence. Each of these architectures plays a unique role in deep learning, and their combined power allows deep learning to automatically learn and optimize the features they extract. They eliminate the need for manual feature engineering. making the process of machine learning far more efficient and effective. These architectures are the building blocks of deep learning, enabling it to learn and optimize automatically. Deep learning isn't just a cool concept, it's a powerful tool that's actively shaping our world. It's like a proficient artist who doesn't need to sketch before painting. It can directly create a masterpiece. This artistry of deep learning lies in its ability to eliminate the need for manual feature engineering. Remember when we had to tell the computer what to look for? Like in image recognition, we'd have to define the edges, shapes, or colors. Not anymore. With deep learning, the system itself learns the significant features. It's like teaching a child to recognize a cat. We don't explain the shape of the ears, eyes, or color patterns. We just show them pictures of cats and they figure it out. Similarly, deep learning algorithms learn from data and optimize the features they extract. Now let's talk about the places where this powerful tool is making waves. First up, computer vision. It's like giving eyes to our computers. From self-driving cars identifying pedestrians to social media apps applying fun filters on our faces, deep learning is at the heart of it all. Then there's speech recognition. It's not just about transcribing what we say, it's about understanding the context, the emotion. It's what makes our virtual assistants like Siri or Alexa seem almost human. Next, we have natural language processing. This is about helping machines understand and generate human language. It's what powers those chatbots that we interact with or the translation apps that break down language barriers for us. Deep learning is also revolutionizing medical image analysis. It can help detect diseases like cancer at early stages, potentially saving lives. It's like having a tireless, super-efficient radiologist who never misses a detail. And let's not forget financial market forecasting. Deep learning models can analyze vast amounts of data, identify patterns, and make predictions. It's like having a crystal ball that can see into the future of finance. From healthcare to finance, deep learning is revolutionizing industries. Deep learning's power lies in its ability to approximate any continuous function, a concept known as the universal approximation theorem. Imagine a kid with an enormous box of Lego blocks. This kid can use these blocks to construct virtually anything they can conceive. A towering skyscraper, a roaring dinosaur, a sleek spaceship. The universal approximation theorem is like that box of Legos for deep learning. It states that a neural network, given a sufficient number of layers, can represent any continuous function. In other words, with enough layers, a neural network can learn to predict or model virtually any pattern or relationship in the data it is given. This theorem is the bedrock of deep learning's power and versatility. It's why deep learning models can tackle such a wide array of tasks, from recognizing faces in photos to predicting stock market trends. If there's a pattern to be found, deep learning can learn to find it. But what about the randomness and uncertainty that often exist in the real world? This is where the probabilistic interpretation of deep learning comes in, specifically in the form of activation nonlinearity as a cumulative distribution function. Imagine you're trying to predict tomorrow's weather. There's no surefire way to know if it'll rain or shine. But you can make an educated guess based on past weather patterns, current atmospheric conditions, and so on. The probabilistic interpretation of deep learning is similar. It acknowledges that there's a degree of uncertainty in the predictions made by a neural network, but it uses the power of probability to make the best possible guess given the available data. In the context of deep learning, activation nonlinearity is seen as a cumulative distribution function. This essentially means that the output of a neuron in a neural network is seen as the probability that a certain condition is met. This interpretation allows deep learning to handle uncertainty and make probabilistic predictions, adding another layer of sophistication to its predictive power. Deep learning's strength lies in its flexibility and adaptability as demonstrated by these concepts. Neural networks are the heart of deep learning, and they come in two types. Dive into the world of neural networks and you'll encounter two main types: feed-forward neural networks and recurrent neural networks. But what sets them apart? Feed-forward neural networks, as the name suggests, are straightforward. They're like a one-way street. Information travels in one direction only, from the input layer through hidden layers and finally to the output layer. There's no turning back or looping around. This kind of neural network is great for problems where the output is a direct result of the current input, like predicting the weather based on today's conditions. On the other hand, Recurrent neural networks, or RNNs, are a different beast. They have a unique feature that sets them apart: cycles in their connectivity structure. This allows them to maintain a sort of memory of previous inputs in their hidden layers. Think of it like a river that loops back on itself, allowing water, or in this case information, to flow around multiple times. This memory makes RNNs ideal for tasks that require understanding of context or sequence, like speech recognition or language processing. They can remember previous words in a sentence and use that information to help understand and process the next words. But why does this matter? Well, imagine you're trying to transcribe spoken words into written text. A feed-forward neural network might struggle because each word is processed independently, with no regard for the words that came before. But an RNN, with its ability to recall previous words, can do a much better job at understanding the context and meaning of a sentence. So there we have it. Feed-forward neural networks, simple and direct, are like one-way streets, while recurrent neural networks, with their unique loops, are more like rivers that cycle back on themselves. Whether it's recognizing speech or processing language, neural networks are the workhorses of deep learning. Deep learning is more than just a buzzword. It's a technology that's changing our lives every day. We've journeyed today through the fascinating world of deep learning, unraveling its core concepts, its intricate details, and its immense power. Let's take a moment to recap our adventure. We started by understanding deep learning as a subset of machine learning, employing artificial neural networks with multiple layers to extract higher-level features from raw input data. We uncovered the magic of how these models can automatically learn and optimize the features they extract, eliminating the need for manual feature engineering. We dived into the universal approximation theorem, which states that deep neural networks can approximate any continuous function. It's like a universal translator for data, transforming it into a language that our machines can understand and act upon. We then explored the different types of neural networks, feed-forward and recurrent, each with their unique strengths and applications. From computer vision to natural language processing, from speech recognition to medical image analysis, and even financial market forecasting, deep learning has found its place, and it's making a significant impact. It's important to remember that deep learning isn't just about the technology. It's about how it's being used to make our lives better, to save time, to increase efficiency, and to open up new possibilities that we could only dream of before. It's about the future and the role we all play in shaping it. So, as we conclude our journey today, let's not forget the profound influence of deep learning. It's a technology that's not just changing our world, but also how we interact with it, how we understand it, and how we envision our future in it. The next time your smartphone recognizes your voice or your email filters out spam, remember that's deep learning at work.